Hello everyone, my name's Gary. Welcome to my channel. For this first particular video that I'm going to make, I'm going to be looking at using Gnu Radio to make a basic FM receiver. Now, I understand that a lot of people have already made similar both websites, blog posts, and YouTube videos doing that. What I'm going to do is I'm going to be looking at it from the perspective of explaining what the various components are doing as they're doing it. I'm also going to give you a general flow for how to build flow graphs to receive different types of signals. And then for future videos, I'll be looking at doing these things in more detail. But what I'm going to be looking at for this particular video is, for those of you who have already made certain frequency demodulator flow graphs, going after FM broadcast signals or for various narrowband signals if you're in amateur radio, things like that. What I'm going to be looking at is you have probably already used either the Quadrature Demodulator block or the wideband FM, the WBFM block. I'm going to be going into explaining the details of how those particular blocks work. So without any further ado, let's get started. So you have your SDR, you're all set up, you have your antenna connected, you're ready to go. What's the process? Here's the process. Step number one, you have to tune. What that means is that you have to be able to get to the frequency of the signal that you're going to try to be receiving. If you're going after the FM broadcast band, that means you're going to be tuning somewhere between 88 to 108 megahertz. If you're going after aircraft communications, you're going to be going between somewhere between 118 and 136 megahertz. If you're going to be going after amateur radio, you'll be tuning to one of the plethora, potpourri, entourage, myriad of bands that amateur radios have access to. So again, very first step is to tune. Now, tuning might be one of two parts. First part is the hardware tuning. You're actively tuning in the RF front end of your SDR. The second part might be software tuning. Once the samples are inside of your computer, then your computer can actually do some tuning within the bandwidth of the SDR, whatever that is, based on its sample rate. The one thing to understand is, in order to receive the signal, it has to be within the bandwidth that your SDR is tuned. And the bandwidth is typically set by your sample rate. So if you're trying to tune to, let's say, 105 megahertz, you're going after something in the FM broadcast band, again, just as an example, and you're using a sample rate of, say, 2 megs, that means that you've got to tune anywhere from 104 to 106 megs, because your sample rate means you're only going to be go plus or minus half your sample rate, so plus or minus 1 meg. So once again, step number one, tune. Step number two, filter. What that means is you're going to be going after a particular signal. Now, later on we'll talk about how to recover multiple signals at the same time. For now, just understand that you have to be able to filter out the particular signal that you want to be able to look at. Whether that's just to be able to look at it, you're going to be doing some measurements on it, or you actually wanted to modulate it, and if it's a digital signal, perhaps be able to break back the bits and decode it. Regardless, step number two is filter to isolate that particular signal, get rid of everything else, all the noise, all the other signals, all the interference, and just be left with that one signal that you want to deal with. Because the next part is step number three, process. And I say process, yes, that's very generic. That sounds like it's just kind of a, wait a minute, that's kind of a blow-off term, isn't it? That just means that you're just looking at it from the perspective of what are you going to be doing next? Well, I say process, and I have to be generic because the next step depends on what type of signal you're trying to go after. If you're going after analog, the next step is to actually demodulate. That's the first step of the process. If you're going after digital, then you might be having to do symbol sync. Again, it depends on the signal. So therefore, anytime you're going after a signal, step number one, tune. Step number two, filter. Step number three, process. Let's get into it. I've opened up Gnu Radio Companion and I've started a brand new flow graph. When you do that, you get these two blocks, the options block and the variable block. Options block is going to tell you the name of the flow graph that you're going to create, as well as it will also create the name for the Python script that's going to be created when you run it. This one block here, variable block, variable is just a generic block, but this one, variable block, is always put in at the beginning. And you notice it says samp_rate. That means that's going to be setting of the sample rate for most of the flow graph. You can actually set it to whatever you want. This is a default that comes with it, so it's one I'm going to use. For this particular one, first thing I'm going to do before I do anything else is I'm going to go ahead and I'm going to do a shift and save as, and I'm going to name it. In this particular case, I'm going to set it to, the name is just going to be basic underscore FM underscore receiver. So again, just basic FM receiver. You can name it whatever you want. You just have to keep the naming convention. You can only use underscores or dashes for this one. However, I recommend that you keep with underscore, or in some case camel case. Camel case would be something like, but most of the time people just use underscore, so I'm going to just keep it as basic FM receiver. Now, the reason I did that, the very first thing, was that when I open up the options block, it also sets the ID. So now the ID is set the exact same as the file name. And the reason that I like to do that is when I actually run this, it's going to create a Python script, a file with a .py at the end as the extension. And so now the file name, the .grc file that I've created, and that .py file will have the same, so they'll be, I can keep them together. It's easier for management. But while I'm here, I can go ahead and set the title. And if your ego is really needing it, go ahead and put your name in there. And now I'm set up and ready to go for adding my components. First component that I'm going to add, I'm going to go ahead and hit the little magnifying glass to open up my little search block, and I'm going to type in RTL. And for this one, I'm going to add in the Osmo SDR RTL-SDR source. And I actually have the option of that or the SOAPy. I prefer the Osmo SDR source. Gives them a little bit more flexibility. So for this one, what I'm going to do is I'm going to leave it as is. However, I am going to need to change the sample rate. And the reason being is that RTL-SDRs want very specific sample rates. The max that you want to do is about 2.5 megs. I'm going to set mine to 2.4 megs. So I'm going to say 2.4, and then the megahertz is E6. That means 2.4 times 10 to the 6. Now, I've actually seen it where some people will do times 10, and then the exponential is star star, so I would be the same thing. I just find it's easier to say 2.4 E6. So I've now set it to 2.4 megahertz, or 2.4 million, and you notice that when I go ahead and close that up, it says 2.4 capital M. That means meg. So I've now set this to 2.4 meg. It's starting with a channel frequency of 100 megahertz, which is right in the middle of the FM broadcast band. Before I'm going to do anything else, I'm going to go ahead and I'm going to add in a frequency sync. So in the search bar, I'm just going to type in FREQ. Right here at the bottom, acute GUI frequency sync. I'm going to add and drag that in. And before I do anything else, I'm going to go ahead and run this. Since it opened up in another window. So here is the window that opened up. And what this says is I'm actually seeing, I actually have this big signal here. That's a 99.1. It's a station that's actually very close to me. Causes me all kinds of problems. And then I have several other stations in here as well. But what this tells me is, I'm getting good samples off of my RTL-SDR source. So I can continue on. As I said before, the very first thing that you need to do is you need to tune. So I'm going to go ahead and I'm going to just, for now, I'm going to select a specific FM station. In this particular case, the one that I'm going to select is 90.9, and again, E6, because it's 90.9 megahertz. So the E6 is for the megahertz. I'm going to come down here, I'm going to set my RF gain. It's at 10. I'm going to go ahead and leave that. That's fine. I'm going to click OK. And I'm going to go ahead and check this one more time. Run it, and let's see if I have a signal here at the center. I do. And so what I have here is this is the station that I'm going to be demodulating. And what I have is I have this one station actually has an analog component. That's this part here in the center. And then I have these two things off to the side, which we call, sometimes called digital shelves. They're called iBox. Stands for in-band on-channel. They're the digital. They're supposed to be the HD. Again, HD, your mileage may vary on that. But what you can see is if I add in some averaging, they kind of become these nice little square shells off to each side of this center part here. What I'm going to be doing for this particular flow graph is I'm going to be demodulating this particular part right here in the center, the analog part. Now, before I go any further, one of the things I want to do is, the next step after this is I need to filter. So question is, how big do I need to make my filter? So I can actually look at this and I can see that the digital shelf starts at about, let's say 110 kilohertz. And then about same thing on the negative side. So I'm going to make a filter that filters out everything except for the center plus and minus 110 kilohertz. So about 220 kilohertz-ish. Okay? So with that, I'm going to close that. And so now I'm going to add in my filter. So for my filter, I'm going to just type in LOW, low. And I'm going to use the FFT low pass filter. I'm going to click and drag that in here. And I'm going to add that to the RTL-SDR source. Open up the properties. And inside the properties, the cutoff, I have two options here. I have cutoff frequency and transition width. The cutoff frequency is, that's the part that I want to make certain grabs the entire signal that I'm going to be looking at. FM stations, at least here in the US, are supposed to be able to deviate up to anywhere from 75 to 82.5 kilohertz. I'm going to go ahead and say about 90. So I'm going to say 90 E3. The E3 is for a kilo. And then remember how I said that I want to be able completely done by the time I get to about 110. So 110 minus 90 is 20. So I'm going to say 20 kilohertz. And then I'm going to click. Oh, I'm going to leave everything else the center. I'm going to leave everything else the same here, the Hamming window and so on. I'm going to cover that in a future video, why you use those particular things. And then at the output here, I'm just, to start with, before I do anything else, I'm going to set up my frequency sync to have two inputs. And then I'm going to take the output of the filter and I'm going to put it into the second input of the frequency sync. And now the reason I'm doing that, when I run this, the blue is the original spectrum. The red is showing the spectrum after it's filtered. And as you can see, I've grabbed this part here in the center, which is the part that I want, and I've gotten rid of everything else. Now you might say, well, wait, I can still see those. Yes, you can. But the difference between the part that's filtered and the part that's not filtered is, if I stop this for just for a second, let's use this. I'm looking at minus 38 dB down to about minus 124 dB. That is a difference of over 80 dB. So that's more than enough. That's plenty. And so now with that, I can go ahead and take this, convert this back into, whoops, into one input, output here. Now that I have the filter set up, one of the things that I can do is I can go in and I can adjust the sample rate or lower the sample rate because I don't need all of it anymore. Specifically, because I've set it now to where the cutoff frequency is at 90 kilohertz, my transition width is 20 kilohertz, that's a maximum of 110. Consider that to be essentially my Nyquist frequency. So if I take that times 2, that would be my Nyquist rate, which is about 220 kilohertz. My current sample rate is 2.4 megs, so if I take 2.4 megs divided by 10, that's 240 kilohertz. I still maintain Nyquist, and it's a nice round number. So I'm going to set that there, and then I'm going to go in, I'm going to do the exact same thing inside of the frequency sync. When I run the flow graph and I look at my frequency sync, I'm seeing only the signal that I filtered on, the original analog signal here, and I'm now between plus and minus 120 kilohertz because my sample rate is 240, so half of that, the Nyquist frequency is half of that, which is 120 kilohertz, so plus minus 120 kilohertz. And I'm set up for the next step, which is step 3, process. The processor for this particular signal is a frequency demodulator. Before I continue on, let me explain how I'm going to build a frequency demodulator. And in order to do that, I'm going to add in a constellation sync at the output of the filter here. When I run this, what I get is a ring, sometimes call it a donut. And that indicates that I'm seeing a signal that is changing with phase over time. What a constellation sync is showing you is it's showing you magnitude versus phase. Magnitude is the distance of these various points from the center. And if I turn on the grid, you can see a little bit better. Here's my center point. And the distance to each of these points is the same, which is forming a circle. If I make it a square, it shows it up a little bit better. And the reason being is that frequency modulation is sometimes called a constant amplitude or a constant envelope modulation method, meaning that its amplitude should not change, it should just be the frequency. Frequency is a change of phase over time. So what I need to do is I need to figure out what that phase change is. In order to figure out the phase change, I need to be able to process consecutive samples one against the other. To do that, get rid of this, I'm going to add in a delay. And then I'm going to add in a complex conjugate. I'm going to set the delay to a value of 1 sample. And at the end here, I'm going to add a multiply block. The output of the filter is going to go directly into one of the input ports. The output of the complex conjugate will go into the other one. So what I'm going to do is I'm going to multiply one sample against the delayed. So in other words, the previous sample, which has also been conjugated, meaning that its phase has been flipped from positive to negative or negative to positive, depending on which way it was. And when I do that, I'm going to show you the complex constellation. Let me go ahead and turn the grid on first. And when I run this, you can now see that the phase is changing. I'm actually looking at the phase changes from one sample to the next. If I pause this, each one of these points, if I zoom in, each one of these points is an angle from the positive x-axis, from the center of the graph on the positive x-axis to this point. That is what I am looking for. That is the phase difference between consecutive samples. That is my demodulation process. The output is still complex, and I want it to be some real value. So the value that I'm going to use is I'm going to use start by using radians. So I'm going to do a complex to arg, or if you like pirates, complex to arg. This will convert it into radians. But ultimately, I really don't want radians either. I want it to be in hertz. In order to do that, I'm going to do a multiply constant in order to just do a units conversion. So let me bring in the multiply constant block. And the value that I'm going to put into this multiply constant block is looking back and understanding that a change of phase over time, well, I already have the change of phase. That's what this section here does. But where's the change in time? Well, the change in time is dividing by the sample period. That's the change in time. Difference between consecutive samples is the sample period. Dividing by the sample period is same as multiplying by the sample rate since they're inversely related. So the first thing I'm going to do is I'm going to take the value and I'm going to multiply by the sample rate. Except it's not the overall sample rate of 2.4 megs, it's a sample rate coming into the beginning here, which is actually 240 kilohertz, or it's sample rate divided by 10. And to emphasize that, I'm going to put this whole thing in parentheses to say that this whole value represents the sample rate coming into this circuit here. The next thing is I've got it in radians. Most people don't deal with radians. We deal with, cycles per second or hertz. So I'm going to divide that by 2 pi or 6.28. Later I'm going to go in and actually change that to an actual much more accurate value of pi, but for now I'm just going to say 6.28. If I leave this as is and I look at a time domain sync, in other words, think of this as a oscilloscope view, a time domain view of this output signal. When I run this and I look at this display, here is my display, here's my time sync up here at the top, and all I'm doing, by the way, is I'm just taking my cursor, putting it inside the graph here, and rolling the mouse wheel forward to zoom in, or zoom out actually. And I've got values that are plus or minus almost 80 kilohertz. Well, if you remember, I said that the deviation of US FM broadcast stations can be anywhere from 75 up to 82.5 kilohertz. What you're looking at is you're actually looking at the raw deviation of the carrier. This is actually in hertz. So if I wanted to, when it's actually at a peak volume, I could actually stop this and measure what the actual deviation is of the signal at any particular point in time. Ultimately, I want this to go into a audio sync. At least on Linux. Windows and Mac is a little bit different. I'm actually not that familiar with Mac. I am familiar with Windows. Windows can be a little bit iffy, but in Linux, definitely, you do not want values going into an audio sync that are greater than plus or minus 1. Otherwise, you'll hear splotchiness or you won't hear anything at all. So I need to get this normalized. And what I'm going to do is I'm going to open this back up and I'm going to set sample rate divided by the quantity 6.28 or 2 pi times my maximum deviation. Now, as I said, maximum deviation can be up to 82.5. I'm just going to make it 85 to give me a little bit of wiggle room. So at 85 E3, I'm going to click OK. When I run this now, notice that I now have nice amplitudes that are contained within plus or minus 1, so I can put this into an audio sync without a problem. And what I just created here, from this block all the way over to this block here, from the delay, complex conjugate, multiply, the complex to arg, and the multiply constant block, is actually contained in one block in GNU Radio. And that particular block is called a Quadrature Demod block. This is the exact same thing as these 5 blocks right here, and exactly the way I have it set up. And I can show that. Let me go ahead and get rid of that. Don't need that anymore. Don't need that anymore. But if you look at the time sync, what I'm going to do is I'm going to take the multiply constant, this value here, copy it, paste it into here, set up a second input on my time sync, and then I'm going to connect the output of my filter into the quad Demod block over to here. And when I run this, these two waveforms should be exactly overlapping. So now if I just turn this off, notice they are exactly the same. It's because they are exactly the same. I've created the exact same circuit inside of the Quadrature Demod block. This is the block, the general FM or frequency demodulation block. It's called Quadrature Demod. I really don't like that name. The term I prefer is called a polar discriminator. Discriminator is typically a circuit that you use for frequency demodulation. Polar discriminator because, again, it's using a polar process. But that's me. Now that I've shown how the frequency demodulator works, in other words, this Quadrature Demod block, I'm going to go ahead and simplify my flow graph. I'm going to get rid of these 5 blocks and just use the Quadrature Demodulator. I'm going to go ahead and set up my time sync back to 1 input for now. Two things left to do. One is I need an audio sync. And you'll notice that the audio sync has a sample rate of samp_rate, and that it's red. It means that GNU Radio is saying, I'm not happy about this. And that's because you're trying to tell your audio card on your computer to go at 2.4 megahertz. I'm pretty certain it won't do that. The fastest I'm aware of any audio circuit is 192 kilohertz. So what I need to do is open this up, and when I look at the drop-down values, it's saying values from 16 kilohertz up to 48 kilohertz. Those are the most common sample rates that are available on audio circuitry in computers. So I'm going to select 48. So let's look at the various sample rates here. I've got my RTL-SDR source, which is coming out at 2.4 megs, goes through the filter. The filter decimates by a factor of 10, downsamples by a factor of 10, meaning it's coming out at 240 kilohertz. The frequency demodulator block does not change the sample rate, so it's still coming out at 240 kilohertz. So I need to go from 240 kilohertz down to 48 kilohertz. A couple different ways that I can do this. The way that I'm going to do this is I am going to use another low-pass filter, FFT low-pass filter. These are red. It's not happy due to the fact that I have this orange means it's a real, the blue means it's complex, and it doesn't like the two being matched together. I'm going to go ahead and open up the properties for this. First thing I'm going to do is I'm going to set the type from complex to float. Next, the output of the Quadrature Demodulator block, my frequency demodulator, is 240 kilohertz. The input of the audio sync was 48. 240 divided by 48 is exactly 5, so I'm going to set my decimation value to 5. The sample rate, that's the sample rate coming into this block, which is 240 kilohertz, or sample rate divided by 10. Next, for the cutoff frequency and transition width, my audio frequency going out is going to be 48 kilohertz. Nyquist frequency for that is half of that, which is 24. So I want the combination, the sum of my cutoff and transition width to be no more than 24. Now, I can get away with a little bit more than that, but for now, let's just assume that that's my hard limit. So my cutoff frequency, I'm just going to say 20 kilohertz. And then the rest of it will be, that's 4 kilohertz, so 20 plus 4 is 24, half of my 48. I'm going to leave the Windows hamming, and I'm going to click OK. And with that, I should be able to run this and hear audio. And again, 1700 Headbangers Ball. We're going to take the output, we're going to take this audio sync, and we're going to do one little thing. But before I do that, let me just point out real quick. I've now made a complete circuit. I've gone from my source, which is connected to my antenna, into a filter, demodulator, another filter, as well as a downsampler to get it set up for the audio sync, and then into audio sync, and I can now fully demodulate the FM broadcast station. Only other thing that I might want to do, for now at least, is add in a block called a deemphasis block. And I want you to think of this deemphasis block as a low-pass filter. On the transmit side, FM broadcasters put in something called pre-emphasis, which is a high-pass filter. And what they do with that is they give more energy to the higher frequencies. Because frequency modulations, it's complicated. It will have more problems. The signal will have more problems that due to the higher baseband frequencies than the lower frequencies. So to get around that, to help to deal with that, they put in a pre-emphasis circuit which gives more energy to the higher frequencies to make it more robust for dealing with the propagation. But what you need to do on the receive side is add in this low-pass filter, this deemphasis circuit, in order to equalize everything again. So I'm going to open this up. Sample rate, well, that's 48 kilohertz. And then this tau value, that's just related to the values of the low-pass filter. In the US, it's 75 microseconds. Overseas, it's 50 microseconds. I'm in the US, so I'm going to use 75. And with that, if I play this again,
the vigorous string performance of the...
And what you it might be hard to hear, but there's actually now a bit more emphasis on the low. The bass is a little bit stronger because of the fact that I've now attenuated or reduced the amplitude of the higher frequencies due to this deemphasis before I did that. So again, I've now made this whole circuit. And the reason that I added in the deemphasis, normally I wouldn't. And one more thing that I wanted to throw in here is this block called the wideband FM receive block. If you've already gone through some of the YouTube videos or interwebs stuff, you may have already learned about using this particular block. It's an all-in-one block, and it's an all-in-one block consisting of the Quadrature Demod, a low-pass filter, and a deemphasis circuit. So what I can do is I can actually create, I've actually created with these three blocks right here, I've actually created this block just in individual components. Now, there's a couple of things that the wideband FM receive does not give you choices to make. The first thing I'm going to start with is I'm going to come up here to the Quadrature Demod. I said that the gain value of the Quadrature Demod block is the sample rate, which is samp underscore rate divided by 10, 240 kilohertz, divided by 2 pi times the deviation. The wideband FM receive block has the deviation set to 75 kilohertz. The other thing is that I actually need to make this times 2 times actual value of pi, much more digits than just 3.14. So what I've done here is, let me close this for a second, is I've done a import block. Let me open this up. Inside of here I've said import math. So I dragged in a block called import, and inside I said import math. And in this value here, what I can do is I can say, instead of 6.2, I can say 2 times math.pi. So the total value is 2 times math.pi times 75 kilohertz. That's the exact values that would be the same inside of this wideband FM receive block. The other thing that I need to change is over here in the low pass filter, I said that the cutoff frequency and the transition width were 20 kilohertz and 4 kilohertz respectively. The way that the wideband FM receive block works is it takes the audio rate, which is 48 kilohertz, in other words, that 240 divided by 5, and it divides that by 32. So 48 kilohertz divided by 32 is 1500. That's my transition width. The other thing that it does is it says, okay, what is half of my audio rate? Half of my audio rate is 24 kilohertz, and then it subtracts the transition width. So 24 kilohertz minus 1500 is 22,500. These three blocks right here will be exactly the same once I have this wideband FM receive block set up. The quadrature, let me open it up. The quadrature rate, that's the sample rate coming in. That's 240 kilohertz. I'm just going to go ahead and say 240 kilohertz. And this decimation value is exactly the same as this decimation value here, value of 5. This is now exactly the same as what I have in these three blocks. And I can demonstrate that by taking the output here, adding another input to here, and then moving this to here, this to here. And for now, I'm going to disable the audio sync. And so now when I run this, the two are exactly overlapping. I turn the red off. The red is from the wideband FM receive block. The blue is from the three blocks, the Quadrature Demod block, the low pass filter, and the FM deemphasis block. So if you're using the wideband FM receive block, well, all you're doing is you're just using these three blocks with those specific values. I hope you've appreciated this little walkthrough, creating the flow graphs, understanding exactly what the various components are doing. In future videos, I'll start going more in depth into several of these blocks, filtering and things such as that. But otherwise, thank you for watching.